A new nuclear fusion reactor record has been set for the quantity of energy generated during a controlled and sustained fusion reaction. A team of scientists in England have shocked the entire industry with the creation of 59 megajoules of energy over 5 seconds at the Joint European Torus, or JET, experiment. How were they able to achieve this feat? What does this mean for the industry and the world at large? Hello, and welcome back to our channel. Stay tuned and ensure you watch till the end to get the answers to these questions. Energy by nuclear fusion has been one of mankind's long-standing goals for decades because it promises to be low carbon, safer than how nuclear energy is now produced, and with an efficiency that can technically exceed 100%. The 59 megajoules of energy generated in December by a team at the Joint European Torus, or JET, facility near Oxford in central England, more than doubled the 1997 record. It would also interest you to know that the energy in 1 kilogram of fusion fuel is approximately 10 million times more than what is contained in 1 kilogram of coal, oil, or gas. How does a fusion power plant operate? Nuclear fusion is the merging of 2 atomic nuclei into 1 compound nucleus. This nucleus then breaks apart and releases energy in the form of new atoms and particles that speed away from the reaction. A fusion power plant would capture the escaping particles and use their energy to generate electricity. Fusion can be controlled in different ways, one of which includes the use of magnetic fields to confine atoms until they are heated to a temperature that is high enough for them to fuse. The fuel for current and future reactors are 2 different isotopes of hydrogen, meaning they have the 1 proton but different numbers of neutrons, called deuterium and tritium. Normal hydrogen has 1 proton and no neutrons in its nucleus. Deuterium has 1 proton and 1 neutron, while tritium has 1 proton and 2 neutrons. When carrying out a fusion reaction, the fuel atoms must be heated until the electrons break free from the nuclei to form a plasma, which is a collection of positive ions and electrons. The heating of the plasma continues until the temperature gets to over 200 million degrees Fahrenheit, or 100 million Celsius. This plasma must then be kept in a confined space at high densities for a long enough period for the fuel atoms to collide into each other and fuse together. To effectively control fusion on Earth, a donut-shaped device called TOKAMAK was developed by researchers. The TOKAMAK uses magnetic fields to contain the plasma. Magnetic field lines wrapping around the inside of the donut act like train tracks that the ions and electrons follow. By injecting energy into the plasma and heating it up, it is possible to accelerate the fuel particles to such high speeds that when they collide, instead of bouncing off each other, the fuel nuclei fuse together. When this happens, they release energy, primarily in the form of fast-moving neutrons. During the fusion process, fuel particles gradually drift away from the hot, dense core and eventually collide with the inner wall of the fusion vessel. To prevent the walls from degrading due to these collisions, which in turn also contaminates the fusion fuel, reactors are built so that they channel the wayward particles toward a heavily armored chamber called the diverter. The diverter pumps out the diverted particles and removes any excess heat to protect the tokamak. A major limitation of past reactors has been the fact that diverters can't survive the constant particle bombardment for more than a few seconds. To make fusion power work commercially, engineers needed to build a tokamak vessel that will survive for years of use under the conditions necessary for fusion. The diverter wall is the first consideration. Though the fuel particles are much cooler when they reach the diverter, they still have enough energy to knock atoms loose from the wall material of the diverter when they collide with it. Previously, JET's diverter had a wall made of graphite, but graphite absorbs and traps too much of the fuel for practical use. Around 2011, engineers at JET upgraded the diverter and inner vessel walls to tungsten. Tungsten was chosen in part because it has the highest melting point of any metal, an extremely important trait when the diverter is likely to experience heat loads nearly 10 times higher than the nose cone of a space shuttle re-entering the Earth's atmosphere. The inner vessel wall of the tokamak was upgraded from graphite to beryllium. Beryllium has excellent thermal and mechanical properties for a fusion reactor. It absorbs less fuel than graphite, but can withstand the high temperatures. The energy JET produced was what made the headlines, but we'd argue it is in fact the use of the new wall materials which will make the experiment truly impressive, because future devices will need these more robust walls to operate at a higher power for even longer periods of time. JET is a successful proof of concept for how to build the next generation of fusion reactors. What does this mean for the industry and the whole world in general? The ITER fusion reactor is going to incorporate the lessons of JET, but at a much bigger and more powerful scale. The data received from the JET experiment is being used for ITER, which is a larger and more advanced version of the JET. ITER is a fusion research mega-project supported by 7 members: China, the European Union, India, Japan, South Korea, Russia, and the USA, based in the south of France, to further demonstrate the scientific and technological feasibility of fusion energy. Ian Chapman, CEO of the UK Atomic Energy Authority, said in a statement, "These landmark results have taken us a huge step closer to conquering one of the biggest scientific and engineering challenges of them all. It is a reward of over 20 years of research and experiments with our partners from across Europe. It's clear we must make significant changes to address the effects of climate change, and fusion offers so much potential. We're building the knowledge and developing the new technology required to deliver a low-carbon, sustainable source of baseload energy that helps protect the planet for future generations. Our world needs fusion energy." This milestone by JET in England has been termed a breakthrough by most media organizations and has also captured the interest of physicists. The JET finding represents significant progress in the understanding of fusion physics, but perhaps more crucially, it demonstrates that the new materials used to create the fusion reactor's inner walls performed as expected. The fact that the new wall structure functions so well sets these findings apart from past milestones and brings magnetic fusion closer to reality. The JET TOKAMAK is the largest and most advanced magnetic fusion reactor currently operating, but the next generation of reactors is already in the works, most notably the ITER experiment, set to begin operations in 2027. ITER is going to use many of the material advances JET showed to be viable, but there are some key differences. First, ITER is massive. The fusion chamber is 37 feet or 11.4 meters tall and 63 feet or 19.4 meters around, more than 8 times larger than JET. In addition, ITER will utilize superconducting magnets capable of producing stronger magnetic fields for longer periods of time compared to JET's magnets. With these upgrades, ITER is expected to smash JET's fusion records for both energy output and how long the reaction will run. ITER is also expected to do something central to the idea of a fusion power plant: produce more energy than it takes to heat the fuel. Models predict that ITER will produce around 500 megawatts of power continuously for 400 seconds, while only consuming 50 megawatts of energy to heat the fuel. This means that the reactor produced 10 times more energy than it consumed, a huge improvement over JET, which required roughly 3 times more energy to heat the fuel than it produced for its recent 59 megajoule record. JET's recent record has shown that years of research in plasma physics and materials science have paid off and brought scientists to the doorstep of harnessing fusion for power generation. ITER will provide an enormous leap forward towards the goal of industrial-scale fusion power plants. Do you think ITER will be able to achieve all that it has proposed? You can let us know in the comments below. Don't forget to like, share, and subscribe to this channel. Thanks for watching, and see you in the next video. Bye-bye.